Welcome back to the Deep Dive. It is February 18, 2026. And today we are doing something a little different. We are not just analyzing the news. We're stepping into the war room.
We certainly are. And frankly, looking at this stack of documents on the desk, I mean, we've got confidential strategic reports from Continental, AWS, ARM, Electrobit, IDIATA, Vigrade for Telex, Technica Engineering, AVL, Horibamira. This isn't just a deep dive. This is a survival guide for the modern automotive industry.
It really is. So let's set the scene for you, our listener. Put your game face on. For the next hour, you are not just a casual listener.
No.
You are a senior technology strategy consultant at a top-tier global firm. You have a meeting in exactly 60 minutes with the chief engineering officer of a major automotive OEM.
And let's be really honest about the context here in 2026. This OEM, they're in trouble. They're bleeding money in R&D, their software launches are consistently delayed, and their physical prototypes are failing late in the development cycle. It's a mess.
A huge mess. And your mission, should you choose to accept it, is to walk in there and deliver a strategic report titled The Global Data-Driven Validation System.
Your job is on the line. Maybe their job is on the line. The stakes are incredibly high.
Sounds intense.
It is.
Yeah.
Because the industry has fundamentally, and I mean fundamentally, changed. We aren't just building mechanical beasts anymore. We are deploying software that happens to have wheels. And the old way of checking if that software works, it's dead.
Completely obsolete. So to prepare you for this high-stakes meeting, we are going to break this down McKinsey style. We're going top-down. We're keeping it MECE.
Mutually exclusive, collectively exhaustive.
Exactly. No fluff, no marketing jargon, just pure strategy. We need to strip it all away and look at the hard engineering reality of 2026.
And we have a massive stack of sources today to do that. We're pulling from the 2026 strategic playbooks of the absolute titans of automotive tech. This is the who's who of the entire ecosystem.
So let's start where any good report starts, the executive summary.
Yeah.
If you are walking into that boardroom, you're standing in front of the CEO, what is the single core problem statement? What is the why?
The problem is what ETS in their documentation calls the scissors effect.
I love a good visual metaphor. So, okay, picture a pair of scissors.
Exactly. Just visualize two blades moving in opposite directions about to cut something. The top blade, the one going up, is complexity.
Okay, define complexity for us in this context.
In 2026, the lines of code in a premium vehicle have surpassed 500 million. It's staggering. But it's not just the code. The number of test cases required for, say, level 3 and level 4 autonomy is in the billion, maybe trillions.
It's an unmanageable number.
It's an astronomical number. And then you layer on top the legal requirements for cybersecurity. That's ASO 21434 and functional safety, ISO 26262. That blade is just going up and up exponentially.
That's the top blade. So what's the bottom blade?
That is resources. And that blade is cutting down hard. Time to market has shrunk from what used to be 48, maybe even 60 months, down to 18 months. You have to compete with the agile Chinese OEMs.
18 months from concept to showroom.
It's brutal. Budgets are flat or shrinking. But the most critical resource that is vanishing, and this is the absolute killer, is the physical prototype.
Right. In the old days, back in 2020, you'd build a fleet of mule cars. You'd drive them around for a year, 1,000,000 miles to find all the bugs.
You can't do that anymore. Think about it. By the time you mold the steel for a physical prototype in 2026, the software version it was originally meant to test is already 6 months old. It's obsolete the day it rolls off the line.
So if you rely on physical hardware to validate your software,
you are validating the past. You get cut by the scissors. You fail. It's that simple.
So the gap between what we need to test, that top blade, and what we have to test it with, the bottom blade, is just widening every single second.
Precisely. And if you stick to the traditional linear model of development, design, then build a prototype, then test it at the end, you are completely and utterly dead in the water.
So the strategic thesis of our report today, the big idea you're selling to that board, is what?
Validation is no longer a quality gate at the end of the assembly line. It is a continuous data-driven engine that runs from the cloud to the edge 24/7. It's about what we call industrialized virtual engineering.
I like that. Industrialized. It implies scale and process. Okay, let's unpack this engine. We organized this deep dive into 4 strategic pillars to solve this scissors effect. What are they?
We need to attack this from 4 angles to be MECE to cover all the bases. Pillar 1 is infrastructure.
Yeah.
The virtual first revolution. The basic question is, how do we test software when the chip it's supposed to run on doesn't even exist yet?
Crucial question.
Pillar 2 is intelligence. This is the generative AI revolution. How do we test for the, kid running into the street in a blizzard without endangering a real kid?
The things you can't or shouldn't test in the real world.
Exactly. Pillar 3 is efficiency, the lab revolution. This is about optimizing the physical testing of things like batteries and motors because, physics still matters. You can't virtualize everything.
Yeah.
And finally, Pillar 4 is connectivity, the data pipeline. This is the plumbing. How do you handle the absolute fire hose of sensor data from a modern car without going blind?
Fantastic.
Yeah.
A really clear structure. Let's dive straight into Pillar 1, the infrastructure revolution.
Right, virtual first. Now, this sounds like a buzzword, I know, but the reports from Continental and Electrobit identify it as the only way to break what they call the hardware dependency trap.
Okay, let's really define that trap for the board. Traditionally, how did software development actually work in an automotive company?
It was painfully sequential. First, the hardware engineers would design the the electronic control unit.
Right.
Little black box.
Right, the brain for the brakes or the engine.
Exactly. They'd send the specs off to a supplier like Bosch or Continental. The supplier would design and build the physical box. They'd ship that box back to the OEM. And only then, months later, could the software team finally turn it on and see if their code even worked.
That just creates a massive, unacceptable bottleneck. You have teams of highly paid software engineers literally sitting on their hands waiting for a FedEx package to arrive.
Exactly. It's insane when you think about it. And in 2026, with the speed of updates required, that latency is fatal to a project. So, okay, the industry tried to solve this. They moved to simulation. Developers started running the code on their laptops.
Which seems logical, but there's a huge catch. And the source material we have from ARM highlights this so vividly. They call it the architecture mismatch.
Right. And this is a critical technical point you need to make in that meeting. Your laptop, the one you're working on, runs on x86 architecture. Think Intel or AMD chips. But the car runs on ARM architecture. The chips in the ECUs, the main vehicle computer, it's all ARM-based. These are two fundamentally different languages. They speak different machine codes.
So to run the car's ARM-based code on your x86-based laptop, you need some kind of translator.
You do. Technically, it's called cross-compilation or emulation. You are essentially using a layer of software to pretend to be a different kind of chip. But here is the massive problem. Emulation is incredibly slow, and much, much more importantly, it is inaccurate.
Inaccurate in what way? The logic is the same, right? A plus B still equals C.
The logic might be the same, but the timing is all wrong, and that is the crucial point.
Okay, explain timing accuracy.
Right.
Why does it matter if a simulation is a few milliseconds off here or there?
In a Word document or a spreadsheet, it doesn't matter at all. But in a real-time braking system, in an airbag deployment system, it's literally life or death. Real-time systems depend on things called race conditions, interrupt latencies, bus timings. If your emulator on your laptop runs the code logic correctly, but gets the timing wrong, you might completely miss a bug that only appears when the real processor is under 99% load and two different tasks try to access the same memory at the same time.
So you validate the code on your laptop, everything looks green, you get the thumbs up,
Yeah.
but when you finally get the hardware and you flash the code to the car,
It crashes. Or worse, the airbag deploys 100 milliseconds too late. This is precisely why the first wave of shift left, this idea of testing earlier using emulation, failed to deliver on its promise. It wasn't faithful enough to the physical reality of the vehicle.
so it created a false sense of security.
A deeply dangerous false sense of security. Which brings us to the 2026 solution.
Which is?
The solution is ISA parity. This is the absolute game changer, and it's being driven by this deep partnership between ARM and AWS.
ISA. That stands for Instruction Set Architecture.
Correct. The strategy is breathtakingly simple in hindsight. Don't translate the code, change the cloud.
What does that mean?
AWS has deployed millions of their own custom-designed Graviton processors in their data centers, and these Graviton processors are ARM-based.
Ah, so now the server in the data center speaks the exact same native language, same machine code, as the chip that will eventually be in the car.
That is the concept of bit parity. You can take the exact binary file, the ones and zeros that you intend to flash into the car's ECU, and you can run it directly on the cloud server. No translation, no emulation, no performance overhead. It's native execution.
And the performance difference is?
What?
What are we talking about here?
We are looking at a 100x speed increase compared to traditional instruction set simulation, 100 times faster. But more importantly than speed, you get environmental parity. You are testing on the same ground truth as the final product. The timing is identical, the behavior is identical.
So you eliminate that false sense of security. What you see in the cloud is what you will get in the car.
Precisely. And Continental has built a whole platform around this concept. They call it the VSDV Composer.
Okay, let's unpack that name. VSDV stands for Virtual Software Defined Vehicle.
Think of the VSDV Composer as a vending machine for virtual car parts. A developer logs into a web portal on Monday morning. They don't have the physical radar chip yet. It's still being designed. They don't have the physical brake controller. But they need to test their new path planning algorithm.
So they go to the composer.
And they click a button that says, Spin up vCar. The system, running in the AWS cloud, instantly creates a containerized environment. It pulls in a virtual ECU for the engine, a VECU for the brakes, a VECU for the dashboard. All of these are just software models running natively on ARM cores in the cloud.
And they're all connected to each other virtually.
Yes, through virtual networks, like a virtual CAN bus. They talk to each other just like they would in the real car. The Path Planner software sends a signal, and the virtual brake controller receives it and reacts.
This really is the ultimate shift left. You are validating the integration of the entire system months, maybe even a year, before the physical chips are even manufactured.
It completely democratizes development. You can have 1,000 developers working on 1,000 virtual cars simultaneously. You could never, ever afford 1,000 physical prototypes. It scales infinitely with the cloud.
But, and I play devil's advocate here, there's always a but. In engineering, the consultant in this meeting needs to be realistic. Not everything can be perfectly virtualized, right?
You're absolutely right. You cannot virtualize the messy, chaotic physics of the real world perfectly. Sometimes you need to touch the metal. You need to see how a real sensor reacts to physical heat soak, or how a real wire harness behaves when it's vibrating at a certain frequency, or how a camera reacts to a very specific weird lens flare.
So you still need a lab.
You still need a lab. And this leads us to the concept of hybrid testing. The report mentions a really specific and clever setup involving AWS Outposts and DSpace.
Okay, what is an AWS Outpost?
This is a fascinating piece of tech. It is literally a refrigerator-sized server rack. It is the AWS cloud, same hardware, same software, same APIs, but Amazon ships it to your facility. You plug it into your wall in your lab.
So you are physically bringing the cloud into your own building.
Physically, you're co-locating the cloud with your hardware. And then you connect that cloud rack directly to a hard, real-time hardware rig like the DSpace Galexio.
Why do you need both? Why can't you just connect your lab equipment to the main AWS cloud over the internet?
Latency. The speed of light is, unfortunately, too slow.
A real bottleneck.
A hard physical limit. If you are testing a critical system like steer-by-wire or brake-by-wire, you can't have the signal go from your lab in Detroit to a data center in Virginia and back again. It takes too many milliseconds. The control loop needs to close in microseconds.
So the DSpace rig, that provides the hard real-time connection to the physical sensors and actuators. It's the interface to the real world.
Exactly. And the AWS Outpost right next to it provides the infinite compute and, crucially, that native ARM environment for the entire software stack. You bridge the gap, you have the massive scalability of the cloud directly and physically connected to the high-fidelity reality of the hardware.
You're creating a seamless cloud-to-edge continuum.
That's the perfect term for it. So for you, the listener, the key takeaway for Pillar 1, the line you need to deliver in that meeting is this. If your client is not using native execution with bit parity, their entire validation strategy is built on sand. They are just simulating a simulation. It's a house of cards.
A very strong, very clear mandate. Let's move to Pillar 2, the intelligence revolution.
Okay. Here we move from the question of how do we run the code to what do we show the code? This is all about generative AI and solving what's called the data deficit.
Wait, hang on. Data deficit. I thought modern cars were collecting terabytes of data every single day. How can there possibly be a deficit of data?
It's a classic quality versus quantity issue, and the report from Fortelix frames this absolutely perfectly. Real-world driving data is overwhelmingly passive.
I mean, it's boring.
Exactly. It's boring. You drive 1 billion miles on the highway, you stay in your lane, the sun is shining, the car in front of you stays a constant distance away, nothing happens. That data is almost completely useless for validating safety-critical systems.
Because you're not testing the limits.
You're not testing anything. To prove an autonomous car is safe, you need to find and test against negative scenarios.
The edge cases, the black swan events, the car that cuts you off, the sudden, unexpected stop, the deer jumping out of the woods at dusk, the child running after a ball from between two parked cars.
Exactly. And statistically, those events are incredibly, incredibly rare. There was a famous study by the RAND Corporation years ago that said you would have to drive for hundreds of millions, maybe billions of miles to encounter enough of these dangerous events to statistically prove that your autonomous car is safer than a human.
You'd have to drive for 500 years. It's just not feasible.
It's impossible. So we can't wait for reality to provide the data. We have to manufacture it.
And that's where AI comes in.
Enter neural reconstruction and generative AI.
Let's break down the workflow that's described by Fortelix. They talk about log-to-scenario technology. What is that?
Okay, imagine a test car is driving around and it captures a 10-second video clip of a near miss at an intersection. In the old days, that was just a video file, a recording. You could watch it, you could show it to your boss, but you couldn't change it.
Right. It's just fixed pixels on a screen. It happened. It's over.
Fortelix's AI ingests that video. It performs something called scene segmentation. It goes through frame by frame and identifies all the objects. That's a truck, and it's moving at 40 miles per hour. That's a pedestrian. That's a red light. It understands the scene. Then it converts that video into a 3D mathematical model, specifically an open standard format called Open Scenario.
So it's basically turning a recording of reality into a video game level. It's now a completely editable virtual world.
Completely editable. And this is where the Gen AI twist comes in. They have a tool they call Cosmos Transfer.
I love the name. It sounds very powerful. How does it work?
It allows engineers to use natural language prompts to manipulate the simulation. It's a paradigm shift.
So like asking ChatGPT to rewrite an email, but you're asking an AI to rewrite a near-fatal car accident.
That is exactly what it is. You take that original near-miss scenario from the real world and you just type in a prompt. Regenerate this exact scene, but set it in Paris at night with heavy snow.
Wow. And the AI handles all the changes, the physics, the visuals, everything.
It handles both. It changes the friction coefficients of the road to match heavy snow. It changes the lighting conditions to match nighttime in Paris. But crucially, and this is the really clever part, it uses neural rendering to create photorealistic sensor data.
Okay, explain neural rendering. Why is that different from, say, the standard computer graphics you'd see in a movie or a video game?
It's a great question. Standard CGI, like you see in Hollywood films, is designed for human eyes. It looks good to us because our brains fill in the gaps. But a car's computer vision system, the AI that's actually driving, it doesn't have a human brain. It looks at raw pixel intensity gradients. It looks at noise patterns. It looks at raw data.
So standard CGI can sometimes look fake to a car's AI.
Exactly. The AI might know it's in a simulation. Neural rendering is a different approach, where the AI is trained on millions of real camera images. It learns the statistical properties of reality, how light reflects off wet asphalt, how camera sensors produce noise in low light. So the images it generates don't just look real to a human, they feel statistically real to the car's perception AI. It tricks the car's brain much more effectively.
That's wild. So you take one single interesting data point from the real world, and you can multiply it into thousands of valuable test cases.
You multiply it by tens of thousands, and this is how you address the unknown unknowns, the things you didn't even know you should be scared of. You can script the AI to fuzz the scenario. You tell it, run 10,000 variations of this scene. For each run, change the speed of the truck by plus or minus 5%, change the pedestrian start time by plus or minus half a second, make the traffic light flicker.
You're systematically hunting for the breaking point of your software.
You are finding the exact millisecond, the exact set of conditions where the software fails. And you do it safely in the cloud, overnight, running on thousands of cores, without risking a single life or a single piece of hardware.
But I have to play devil's advocate again here. We've all seen AI make mistakes. It hallucinates. It can create things that aren't physically possible. How do you ground this in reality?
And that is the perfect transition to the critical counterbalance that's provided in the reports from IDIATA and Vigrade. Their warning, plastered all over the source material, is simple and timeless. Garbage in, garbage out.
Meaning, if the underlying physics of your simulation are wrong, then all this amazing generative AI is just creating beautifully rendered photorealistic lies. The validation is worthless.
Exactly. If you ask the AI for snow, and it draws pretty white pixels on the screen, but the virtual car doesn't slide when you slam on the virtual brakes, you aren't testing anything. You're just watching a cartoon.
So how do you ensure the physics are real? How do you validate the validator?
IDIATA has a really rigorous multi-step validation loop. It always starts with track testing. They take the real physical car, the Audi, the BMW, the Ford, and they take it to their proving ground in Spain, and they drive it to the absolute limit.
J-turns, emergency braking, slalom courses, hitting bumps at speed.
Everything. They instrument the car with high-precision GPS, gyroscopes, accelerometers. Then they take that car off the track and put it on something called a K&C rig.
K&C, what does that stand for?
Kinematics and compliance. This is a massive, complex machine. It physically grabs the wheels of the car and twists and pushes them. It measures with incredible precision how much the suspension bends, how the tires squish, how the chassis flexes under different loads.
They are essentially creating a complete physical fingerprint of that specific vehicle's dynamics.
A perfect description. A fingerprint of the physics. Then they take all that data and they go build a virtual model in a software tool called VI Carrial Time. And they painstakingly tweak the parameters of the virtual model, the spring rates, the damping coefficients, until the virtual car's output perfectly matches the real-world data from the track and the K&C rig. They call this process model correlation.
So the winning strategy for our consultant listener is a kind of hybrid approach, a synthesis of these two ideas.
Yes. That's the key recommendation. Use the powerful generative AI tools for the environment to create the snow, the rain, the unpredictable traffic, the photorealistic visuals, but use a rigorously validated, track-correlated model for the ego vehicle, the car you are actually testing. Do not let the AI hallucinate your own car's physics.
High-fidelity world meaning a high-fidelity car.
Got it.
Okay, that's a huge pillar. Now let's pivot to pillar 3, the efficiency revolution.
Right. We are leaving the clean, virtual world of the cloud now. We are putting on our safety glasses and our steel-toed boots, and we are walking into the physical battery lab.
Because no matter how good your software is, you still need to test the chemistry and the mechanics. Physics is undefeated.
And batteries are the single biggest bottleneck of the entire electric vehicle transition. They're dangerous, they can catch fire, they are heavy, and they are painfully slow to test. You have to age them, you have to run them through thousands of thermal cycles. It can take months, even years.
There is a really shocking statistic in the AVL report regarding OEE. Can you share that?
Yeah, OEE stands for Overall Equipment Effectiveness. It's a measure of how productive your expensive lab equipment is. The industry average for battery lab OEE, according to AVL, is around 31%.
Let that number sink in for a second. A single battery test bed can cost millions of dollars. And you're saying it sits idle or is otherwise non-productive for 69% of the time.
It's a financial and engineering disaster, and the main culprit is usually a rigid, calendar-based, push-based scheduling system.
The Outlook calendar method. I booked the test cell for Tuesday at 9 a.m. for Project X.
Right. That's exactly it. You book the test bed for Tuesday at 9 a.m., but then Monday afternoon you find out the prototype battery for Project X isn't ready, or the cooling pump on the rig is leaking, or the technician who knows how to run that specific test calls in sick.
So the multi-million-dollar test bed just sits empty.
It sits empty, and you can never get that time back.
Right.
The solution AVL proposes is a complete shift in mindset to queue-based planning, a move to a pull system.
Okay, explain how this changes the workflow for a lab manager.
Think of it less like a rigid calendar and more like a print queue, or even better, like Uber for lab tests. You have a central backlog of all the tests that need to be done for all projects. The central lab management system knows the capabilities and status of every single test bed. It knows bed 1 can handle 800 volts and has a thermal chamber. Bed 2 can only do 400 volts.
So the system acts as an intelligent dispatcher.
Correct. When bed 1 finishes its current job, it doesn't sit and wait for its next scheduled appointment. It automatically pings the queue and says, I am free. I am an 800-volt bed. Give me the next highest priority 800-volt job from the queue.
So if the battery for Project A isn't ready, it doesn't wait. It automatically grabs the battery from Project B that is ready.
Instant utilization. It completely eliminates that waiting for input downtime, which is the biggest killer of OEE. But AVL goes a step further, and this is where it gets really smart. They used AI aging prediction.
This is the early stop strategy. I found this absolutely fascinating.
It is. So battery aging is a painfully slow process. To prove a battery will last 10 years or 150,000 miles, you usually have to cycle it for months on end in a lab. But the degradation of a battery follows complex but ultimately predictable electrochemical patterns.
You're talking about the knee of the degradation curve.
Exactly. There is a point where the performance starts to drop off a cliff. Human engineers are naturally conservative. We have a tendency to run the test until the battery is well and truly dead, just to be absolutely sure.
Which wastes weeks or even months of valuable testbed time.
AVL's AI models are trained on data from tens of thousands of previous battery tests. The AI monitors the derivative of the data in real time. It's watching the rate of change of things like internal resistance. It can see the knee of that curve coming long before it actually happens.
So it can predict the future.
Their data shows you only need to run the physical test for about 60% to 80% of the intended duration,
And the AI can accurately extrapolate the rest of the battery's life.
with less than 2.5% error, so you can confidently stop the test, pull that battery off the rig, and start the next test in the queue. You have just effectively increased your lab's capacity by 30% or more without buying a single new piece of equipment.
That is pure operational excellence. And there is one more efficiency hack in the documents, this one from Hariba Mira. They call it scenario condensation.
Right, this is their Mobius platform, and it attacks the boredom problem of physical testing.
We talk about boring data in the virtual simulation world. This is the physical equivalent boring driving in the real world.
That's it. If you are doing a durability test on an electric powertrain, you might have a test cycle that's based on a 9-hour real-world drive. But if you analyze that data, maybe 7 of those hours are just cruising at a constant speed on a highway. That doesn't really stress the motor. It doesn't heat up the inverter.
It's wasted energy and, more importantly, wasted time on the expensive test rig.
Mobius is a tool that analyzes that raw drive data. It mathematically identifies and cuts out all the low-stress periods. Then it stitches together all the high-stress events, the hard accelerations, the steep hill climbs, the heavy regenerative braking events into a much shorter cycle.
It's like creating a greatest hits album of mechanical and electrical stress.
That's a perfect analogy, a condensed cycle. They can turn a 9-hour real-world drive into a 3-hour test cycle that inflicts the exact same amount of fatigue damage on the components.
That's a 70% time saving on that specific test.
A massive saving. And when you combine that with the cube-based planning and the AI early stop, you are looking at potentially tripling the effective throughput of your physical lab. That is the efficiency pillar.
Incredible gains. Okay, let's move to the final, crucial pillar. Pillar 4, the connectivity revolution. The plumbing.
The plumbing, exactly. We've talked about creating data in Pillar 2 and processing it efficiently in Pillar 3. Now we need to talk about the fundamental problem of just moving it around.
This is the domain of Technica engineering in our source documents.
Yeah.
And the problem they identify is the bandwidth explosion.
As we move towards L3 and L4 autonomy, cars are becoming rolling video production studios. They have 8, 10, 12, 4K cameras. They have LiDAR point clouds generating millions of points per second. They have high-resolution radar data. It is an absolute fire hose of information.
And the standard vehicle networks, the old CAN bus or even standard automotive Ethernet, are just completely choking on this data. They can't handle it.
Not even close. And Technica highlights a specific nightmare scenario for validation engineers, the black screen issue.
Paint the picture for us. What is that?
You're a validation engineer. You are out on the test track, testing a new self-driving feature. You're approaching an intersection. Suddenly, the system disengages, the screen goes black, the car hands control back to you with an alarm.
And the big question is, why?
That's the million-dollar question. Was it a software bug in the perception stack? Was it a loose cable on camera 3? Did the main computer overheat? If you weren't recording all the raw sensor data at that exact millisecond, you have absolutely no idea. You are flying blind.
But recording all that raw data from all those sensors requires massive storage and massive bandwidth.
And that's where a technology called SerDes comes in.
SerDes. Spell that out. S-E-R-D-E-S.
It stands for Serializer Deserializer. It's the core technology used in high-speed automotive data standards like GMSL, which is Gigabit Multimedia Serial Link, or FPD link. It's what allows you to shoot uncompressed high-definition video over a simple, cheap, twisted pair cable.
Okay, but to validate the system, you need to be able to tap into that cable and see the data.
You need a capture module. It's essentially a man-in-the-middle hardware device. It's a small box that sits physically between the camera and the ECU. It splits the signal perfectly. One copy of the data goes to the car's computer so it can drive. The other copy goes to a high-speed data logger for analysis.
So it's like a wiretap. You're in spy mode.
You're in spy mode, exactly. But here is the critical technical detail you need to mention in your report. Lossless JPEG compression.
Why lossless? Why not just use a standard compression like MP4, like a GoPro camera uses? That saves a lot more space.
Because MP4 is a lossy compression format. To save space, it throws away data. It smooths out details. It averages colors. To a human eye, it looks fine. But to a computer vision AI, those tiny compression artifacts can look like obstacles. Or even worse, they can hide the details of real obstacles.
So if you train or validate your perception AI on compressed video, you are basically training it on bad, corrupted data from the start.
You are. It's another form of garbage in, garbage out. Technica uses a specific type of lossless compression that can cut the storage size in half, but it guarantees bit-perfect reconstruction of the original image. You lose absolutely nothing.
And the other critical factor they mentioned is timestamping.
Oh, this is huge. You need PTP Precision Time Protocol, ideally the automotive version, which is GPTP.
Explain why timing is so incredibly hard and so important here.
A car moving at highway speed travels about a foot in 10 milliseconds. Now imagine your LiDAR data says, I see an obstacle at time X, and your camera says, I see an obstacle at time Y. If there is a 10 millisecond drift between their internal clocks, the sensor fusion algorithm, the part of the brain that combines their inputs, fails, it might think there are two obstacles instead of one, or it might think there are none.
The car gets confused. It can't build a stable picture of the world.
Exactly. Technica's hardware ensures hardware timestamping right at the point of capture. Every single packet of data from every sensor is stamped with a globally synchronized atomic clock time. It aligns the world perfectly for the fusion engine.
Okay. Now, there's one last concept in this connectivity pillar. It's sort of the holy grail of large-scale validation. Shadow mode.
Ah, yes, shadow mode. This is where you essentially turn your entire customer fleet into your virtual test team.
How does it work in practice?
Let's say you have developed a brand new automatic emergency braking, or AEB, algorithm. You've tested it in the cloud using bit parity, like we talked about in Pillar 1. You've thrown millions of Gen AI scenarios at it from Pillar 2. But you are still, understandably, a little nervous to give it full control of the brakes in millions of customer cars.
Very understandable.
So you push the new algorithm out via an over-the-air or OTA update to, say, 100,000 customer cars. But you switch it to silent mode, or shadow mode.
So it's running in the background on the car's computer, but it's not actually connected to anything.
It receives all the real-time sensor data, it processes it, it makes a decision, it decides, based on this input, I would slam on the brakes right now. But the virtual wire to the brake actuators is cut. It just logs its decision and the sensor data that led to it.
And then the crucial part is it compares its decision to what the human driver actually did in that same situation.
Exactly. This is what's called divergence analysis. You collect the data from the fleet.
Shadow mode says, brake. But the human driver kept driving and nothing bad happened. What does that tell you?
The algorithm panicked at a plastic bag blowing across the road. It was a false positive. That's bad. You need to retrain it.
Okay.
Scenario B. The human driver slams on the brakes to avoid a fender bender. You look at the logs and see that your shadow mode algorithm wanted to brake 500 milliseconds earlier than the human.
The algorithm works. It's better than the human.
And you can run this analysis across millions, even billions of miles of real-world driving without ever risking a single collision.
It is the ultimate continuous validation loop. And once the divergence rate, the number of disagreements, drops to virtually zero, or better yet, when you can prove the shadow mode consistently outperforms the average human, then you can confidently flip the switch. You make it active.
That is the complete data pipeline: infrastructure, intelligence, efficiency, and connectivity.
We have built the cathedral. Now it's time to zoom out for the strategic synthesis.
Right. Our listener is about to walk into that boardroom. They need to give the CEO the 30,000-foot view, the lay of the land. What is the global competitive landscape in 2026?
The world has, it's really fractured into three distinct strategic camps, and you need to explain this clearly. Camp 1 is China. They are the speed kings.
What characterizes the Chinese approach to validation?
Two things: vertical integration and automated calibration. The ETAS reports we have show a massive adoption of AI-based tuning and calibration tools in China. They don't have teams of engineers manually tweaking engine maps or suspension settings anymore, and AI does thousands of iterations in simulation overnight. They prioritize speed and iteration above all else. They will launch a good enough car and then patch it with OTA updates every 2 weeks. Move fast and fix things later. That's the mantra. Camp 2 is Europe. And they are. They are the compliance guardians. Look at the source materials from IDIATA and the new ECAVA, the EU Digital Vehicle Initiatives. They're obsessed with standards ISO 26262, ISO 21434, and digital sovereignty. They focus on that validated model we talked about. They want to be fast, but they refuse to compromise on the deep physics correlation. Their approach is slower, more deliberate, but their validation is arguably more robust. And finally, Camp 3 is North America. The cloud giants. This is the AWS and Tesla approach. It's all about the software ecosystem. They view the car as just another edge device for the cloud, like a smartphone. They're pouring billions of dollars into massive AI compute clusters and end-to-end neural network models. They're making a huge bet that raw compute can solve the complexity problem.
Three very different philosophies. So what is the final recommendation when the CEO asks, what do we do? What's the bottom line for your report?
The one single mandate is bit parity.
Make it crystal clear for them.
To survive in 2026, the OEM must mandate the delivery of virtual ECUs, VECUs, from every single one of their suppliers. Period. End of story. If a supplier comes to you with a physical black box and says, trust me, the software inside works, you show them the door.
No more black boxes.
No more. You demand the virtual twin. You demand the ability to run their code in your cloud, on your CI/CD pipeline, on your schedule.
If you can't test it continuously in the cloud, you can't scale it. You can't ship it.
Precisely. The core recommendation is to dismantle the wall between the IT department and the engineering department. Validation is now a computing problem. It is a data problem. It is no longer just a mechanical problem.
Because that scissors effect is coming for everyone, regardless of which region they're in.
And only the companies that are truly data-driven will survive it.
Expert, before we wrap this up, I want one final provocation. Give our listener, our consultant, something memorable to say at the very end of the meeting. A thought grenade to leave on the boardroom table.
Okay, we've spent this entire hour talking about how to validate the vehicle. But here's the thought grenade. The very definition of a vehicle has fundamentally changed. It is no longer a hardware product that contains some software. It is now a software release cycle that just happens to be wrapped in hardware.
Meaning what? Unpack that.
Meaning the entire power dynamic has inverted. In the past, the software had to fit the car. The hardware was fixed. The engineers would say, here is the suspension, now make the ABS software work with it. In 2026, the car must fit the software. If your data pipeline, your shadow mode analysis, your Gen AI scenarios tells you that your camera and radar sensors can't handle enough of the edge cases to be safe, you don't just patch the code anymore. You change the car. You tell the hardware team to move the sensors. You tell them to change the suspension because the vibrations are creating too much noise in the data.
Wow.
The validation team is now the design team. The data is the boss. So the question you leave the CEO with is this. Are you ready to let the data tell you that your core car design is wrong?
That is a very powerful and probably uncomfortable place to land. The data is the boss. Consultant, you have your report, you have your 4 pillars, you have your strategy. Now go save that company.
Good luck. You're going to need it.
Deep dive complete.